Assalamu alaikum students, this is Talha Akram, and in this lecture we will be discussing the full wave rectification. Now you already have the basic concept of half wave rectification, but in the full wave rectification, the DC level obtained from a sinusoid input can be improved 100% compared to the half wave rectification. Coming to the figure 2.52, that we have some input signal which is a sine signal having the magnitude V of m for the positive half cycle and the magnitude minus V of m for the negative half cycle. Now we developed a bridge circuit here in which for the positive half cycle we will be getting a full wave, and for the negative half cycle again we'll be getting the full wave. So this is a combination of 4 diodes D1, D2, D3, D4 with the resistance R in the center, and we'll be getting the output voltage V0 from the resistor R. So for the positive half cycle, this diode will be on and current will follow this path, and this diode will be on, whereas two diodes D1 and D4 are off and in the non-conducting stage. So from the figure 2.54 we are considering the first half cycle, which is 0 to t by 2. For the positive half cycle, this will be off and the current will follow this path, and here again it is disconnected because it will be reverse bias. So the direction will be this and this. So the drop here is 0 and the current follow this path, and D2 and D3 diodes are in the on state. So for the negative half cycle, this one from t by 2 to t, we'll be getting the wave like this. The current will follow this path, this will be on, again this one because it will be off, and this one. So for the positive half cycle, for the negative half cycle, D1 and D4 are in the on state, whereas D2 and D3 are in the off state. So this is the flow which you can see in the figure 2.55. This is a conduction path for the positive region of input signal V of I. This is the input signal V of I. So for the positive half cycle, again this is closed and the current will follow this path, and the voltage will drop here, and this diode is also closed, and this is the ground. So this is the path for the negative half cycle. The output will be same like the input for the positive half cycle. That it will start because the diode is because the diodes are ideal diode, so at potential 0 volts diode will be in the conducting stage. So this is the input signal and this is the output respectively. So for the positive half cycle, or for the upper lobe 0 to t by 2, we are getting the same signal 0 to t by 2 for the input voltage Vi, and here the output voltage is V0, and we are getting the V0 here. Now in the negative half cycle, this one, for the negative half cycle having potential minus V of m, the diodes, these two diodes, this one and this one, are in the on state, whereas the other two diodes which were previously in the on state, now they are in the off state. So the current will follow this direction and you are getting the drop here. So because the signal is positive and negative here, again we are getting the positive here and negative here, so diode will be in the upper side of the axis and having the same magnitude V of M, which is this one. So for the positive half cycle we are getting the same signal, like having the same magnitude like the input signal. So 0 to t by 2 is this lobe, whereas t by 2 to t is this lobe. So we are getting two positive lobes for one complete input sine signal. So this is the input signal and this is the average DC value of output signal. VDC is equal to 0.636 Vm. We already knew that V of DC in case of half wave rectification is 0.636 divided by 2. So for the half wave rectification, and for the full wave rectification it's 0.636 Vm. And let me write the Vm here. So we are getting a higher DC average value because of this full wave rectifier, and this is also called a bridge network. Okay, since the area above the axis for one full cycle is twice that obtained for a half wave rectification system, the DC levels also been doubled, same like this what we have discussed just right now. VDC is equal to 2 into 0.318 Vm. This is equivalent of VDC is equal to 0.636, or it will be same like this. VDC is equal to 0.636 divided by 2, and I have divided this number with 2 because in the half wave rectification this lobe is complete, but for the second half cycle we are getting the zero signal, so that's why it's divided by 2. So if the silicon diode is utilized instead of ideal diode, then our final relation will be input voltage minus drop of diode 1 minus output voltage V0 minus drop of diode 2 is equal to 0. This is the rise in potential and these are the drops. Rise in potential, summation of rise and drop is equal to 0, or rise is equal to drop. So according to KVL, V0, or this is equivalent of Vi minus V0 minus 2Vk, this is equal to 0. So from this equation we are getting output voltage V0 is equal to Vi minus 2Vk, and because now the peak is different. Before the peak was Vm because we have used the ideal diode. Now the peak is Vm minus 2Vk, and this is the pictorial view of what we have written here. For the positive half cycle, this is the first drop. Vk is equal to 0.7 volts because this is silicon diode. If you are using the germanium diode, then Vk is equal to 0.3 volts. So for the positive half cycle, first drop will be here and Vk is equal to 0.7 volt, whereas the second drop is here. Vk is equal to 0.7 volt for the positive half cycle. So total drop will be 0.7 plus 0.7 is equal to Vm rise in potential minus 1.4 is the output voltage V0. This is the maximum value, which is Vm. Let Vm is equal to 20, and then maximum value will be 20 minus 1.4. So this is equivalent of 18.6. So this is the maximum potential we are getting if we are in the bridge network when we are using silicon diodes instead of ideal diodes. The peak value of the output voltage V0 is therefore V0 max is equal to Vm minus 2Vk, and Vk can either be silicon or the germanium. So for situation where Vm is greater than 2Vk, the following equation can be applied. As we already knew that if Vm is less than 2Vk, then the diodes will never be in the on state. So Vm should be and must be greater than 2Vk. So VDC is the average DC value of this full wave rectifier. It must be here somewhere. This is the average DC value. Average DC value. It is 0.636 into Vm minus drop of 2 diodes. Hope you are getting the point here, that this relation 2Vk is just because of the inclusion of real diodes, which may be silicon or which may be germanium. So we 0.3636 multiplied by Vm minus 2Vk. Now full wave rectifier can be used in the center tap transformer. The concept is the same. Here we have a center tap transformer. We have 2 diodes in the same direction. D1, this is diode D1, this is diode D2, and we are getting the output here V0 at the resistor R. So this is the input signal Vm, this is the Vm signal here. We are applying the Vm signal here, and for the positive and negative half cycle we are getting the output waveform. 2 diodes in the center tap transformer used during the interval T is equal to 0 to T by 2 for the positive half cycle, or for the upper lobe we have diode D1 is on, because the cycle will be like this, and it will be open circuit. So the only wave we are getting here is in the upper portion, and the diode D2 is off for the positive half cycle. Whereas for the negative half cycle, this one, for the negative half cycle, we are just reversing the potential here, positive negative positive negative. So this will be D2 will be on, and we are getting the output again at resistor R, and it will be in the off state because they are disconnected, and the current will not flow here. Current will not flow here. The only direction is this one. So for the positive half cycle, what we are getting here, for the positive half cycle we are getting here this loop, and the output is generated here at Vm, having the maximum value of Vm from 0 to T by 2. Similarly, for the negative half cycle, T is equal to T by 2 to T, what we are getting here for this negative half cycle, this is positive negative positive negative. So waves will be generated in both the parts, but because the circuit is open here, so the current will flow only in this direction. We are getting the output here across the resistor R. So this diode is on, this diode is on in the negative half cycle. So this is the output. So because positive here, negative here, and we are following the proper direction, so the output waveform will be on the positive side, and this is what we got here for the negative half cycle, having the period starting from T by 2 and ending at the time period T for the lower lobe. So this is the output waveform, and the average DC value will be same like what we discussed in the previous example. VDC is equal to 0.636 into VM minus 2VK. So it will be here somewhere. So coming to example 2.17, which is quite tricky because we have replaced two diodes here with the resistors. So determine the output waveform for the network of figure 2.64 and calculate the output DC level and the required PIV of each diode. So coming to the waveform, this is the waveform. This is the waveform. The VM is given 10 volts here, minus VM here in this direction, and it's the sine signal. So this is the circuit, which is a bridge network. Definitely we have two diodes. Let this is diode D1 and this is diode D2, and we have attached three resistors here. One we are using for the output, whereas two other resistors we have connected with the ground. So and we first, as a first step, we need to transform this circuit into some other circuit, like this one. But prior to that, we need to connect and disconnect the diode according to the input signal applied. So coming here, for the positive lobe and having the maximum voltage of 10 volt, we are using the ideal diode. So 0 to T by 2 is the time period. So for the positive half cycle, this will be on and this will be in the off state. So the direction will be like this and this. So the current will flow and this will be off. So the current will flow in this direction. At this node, current is divided into two. One current will one path is this one from here to here, and the second path is this one. So from this figure you can see 2 kilo ohms resistance from where we are getting the output voltage V0, and this resistor are in series. So this is the changed form or revised form of a circuit. 2 kilo ohm, this resistor is this one. Let this is R1 and the R1 is here. Let this is R1, this is R2 and this is R3. Okay, and the this is resistor 2 and this is resistor 3. So for the positive half cycle, resistor 1 and resistor 2 are in series, you can see from here, whereas the resistor 3 is in parallel with these two resistors 1 and 2. So for the positive half cycle, we are getting the potential V0 at resistor R1, and these two resistors are in series. Both are having the same value, 2 kilo ohms, 2 kilo ohms. This means that the applied voltage, applied voltage is maximum applied voltage is 10 volts. So 5 volt will be dropped here and the remaining 5 volt will be dropped here. So otherwise you can directly apply the voltage divider rule, in which you can easily find out the value, which is 10 into 2 divided by 2 total resistance 2 plus 2, which is, let me write at out using the voltage divider rule, which is V0 is equal to applied voltage, this which is Vi multiplied by the resistor where you want to find out the voltage, this is 2, and divided by 2 plus 2. Okay, so the applied voltage, sorry, the final voltage is 5 volts. Otherwise you can also directly divide the total voltage divided by 2, because both resistors are having the same value. V naught max is equal to half Vi max, which is 1 by 2 into 10 volts is equal to 5 volts. This is what we got here using the voltage divider rule. This is voltage divider rule. So for the positive half cycle we are getting the value of 5 volts, and that up to 0 to T by 2. Now coming to the negative half cycle, let me clear the screen. Okay, for the negative half cycle, this diode will be off, whereas this diode will be on state. So let me convert this thing here. This is positive, this is negative, and the direction of a current will be like this. So this diode will be off and this diode will be in the on state. So we are getting the output again at point at resistor 2 kilo ohm, which is resistor 1, and we are getting the value 1 volt. So the circuit will be same. Now this time, if this is 1, this is 2, and this is 3. So in this case resistor 3 and resistor 1 are in series. Resistor 3 and resistor 1 are in series, whereas resistor 2 is in parallel. So again apply the voltage divider rule, which is 10 into 2 kilo ohms divided by 2 plus 2 kilo ohms. This is equivalent of again 5 volts. So for the lower lobe, or for the negative half cycle, again we are getting the 5 volts, peak of 5 volts. So the average DC value is 0.636 into 5 volts is equal to 3.18 volts. So the average DC value is 3.18 volts. So from the this slide, now you have a clear understanding about the full wave rectification, that when you want to double the potential or double the voltage of half wave rectification, then you will be needing a bridge network or center tap network, in which you will be getting a full wave and positive low for both the cycles. The upper cycle we are getting the positive low, for the lower cycle again we are getting the positive low with the average DC value of 3.18 volts. In the coming lecture we will be discussing the clippers, in which you will learn how we can truncate the wave as per requirement. Thank you.